I believe, and I'm really looking forward to hearing about that. Thanks.
Yeah. Okay. Thanks, Arthur. Hello, everyone. So today I'm going to talk about policy gradient methods. And we are going to talk about pros and cons of policy gradient methods. And specifically, we're going to focus on how we can do a little bit more smarter exploration, as Thorsten mentioned, and robustness in policy gradient methods. So this is a joint work with my former colleagues at Microsoft Research, Alec Aguar, and Michael Hinoff, who's now at Facebook AI, and Sean, who's a professor at UW and also a principal researcher at Microsoft Research. Okay, so policy optimization approach, specifically incremental policy optimization approach, is probably one of the most popular paradigm that people use in practice. Right? So people use this incremental policy optimization approach for solving this extremely challenging board game Go, and people use optimization, policy optimization approach, especially policy gradient methods for training an agent to play this Dota game. And recently, the OpenAI is also using policy gradient methods to train a physical manipulator to play this Rubik's Cube. So pretty much for all these applications, policy gradient methods and incremental policy optimization approach are basically the most popular method. So in this talk, we are trying to sort of answer this question. Can we design a provably correct policy gradient algorithm, and also without lose the advantage, the practical advantage of policy gradient methods? So to answer this question, we're going to look at this particular formulation of Markov decision process. So this is called infinite horizon discounted Markov decision process. So here you always have two components. So you have a learning agent and you have an environment, and the learning agent will interact with the environment by computing the action based on the current state of the environment. So here the state basically describes the current situation of the environment, and then the agent makes a decision based on the current information about the environment. And then the agent going to send the decision and action to the environment, and then the environment will evolve accordingly based on the underlying Markovian transition, which is unknown to the learner. And it will send a one-step immediate reward back to the agent, and also send the next state to the agent. And then this process goes on for, let's say, infinite many steps. And our objective function here is to find this policy pi that maximizes the expected total future reward. Right? But here we're going to add this discount factor, where we're going to discount the future rewards in the future steps. But this is a very standard objective function. So we want to find a policy, a procedure, a behavior that can make decisions sequentially based on the information about the current environment. And our goal is to find this strategy that maximizes the expected total long-term reward. So particularly in this talk, let's probably imagine that we can only reset the agent to a fixed state. Okay, so we allowed to do multi-episodes interaction with the environment, but every time when we reset the system, we always reset it to a fixed state. So imagine you're playing a video game, you're playing a board game, right? So we always reset to the initial state of the game. We cannot reset to any part of this in the middle of the game. We can only reset to a fixed state. So the reason that we try to emphasize this assumption is that this basically makes the problem much harder, because now you really need to do exploration. Right? So imagine your initial configuration, your initial state is really, really far away from the goal configuration or the goal state. And this forces us to do exploration because we really needed to figure out a good way to navigate it from initial state that is pretty far away from the goal state. But the results will generalize to the more general setting where you have a fixed initial state distribution rather than a fixed delta distribution over a particular point. Okay. So we're going to focus on policy gradient methods. which are probably one of the easiest, simplest approach, reinforcement learning approach that you would try in practice. So here we're often going to parameterize our policy, right? So here maybe we can use a neural network to parameterize our policy, which takes the state as input and outputs an action, outputs a decision. Right? And we're going to use gradient descent approach to incrementally update the parameters of this neural network, for instance, which is represented by theta here. And remember, we talked about the objective function, right? So the objective function is super well defined. It's just the expected long-term total reward. And since we have a very well specified objective function, we can basically just compute the gradient with respect to the parameters theta here. There are closed forms that you can basically derive for this policy gradient, this gradient of this objective function with respect to the parameter theta. And with that gradient, the simplest thing that we can do is just do gradient ascent here, right? Imagine that we are optimizing, we are maximizing the reward. So we do gradient ascent. And this is a very valid reinforcement learning algorithm indeed. And algorithms such as reinforce, TRPO or PPO, they are basically variants of that. Now, of course, you can do a little bit more here, right? For instance, you can do some sort of preconditioning. So let's see, you use some Fisher information matrix to do preconditioning of the gradient. And then you follow that preconditioned gradient step. So this is called a natural policy gradient. That borrows ideas from the natural gradient descent algorithm. And so indeed, those practical algorithms that such that TRPO and the PPO, they're basically variants of this natural policy gradient. Okay. And in this talk, we are going to focus on this natural policy gradient update rather than the vanilla gradient update. Okay, so what is the main advantage of policy gradient methods? Right. So I think the main advantage is the strong organostic guarantee that we can get from policy gradient methods. So now imagine that you are running some policy gradient methods. I hand you a policy class. So let's see, every policy in this policy class is parameterized by some, 2-layer feed-forward neural network, for instance. Okay, and there is no way you can tell that this policy class, this parameterized restricted policy class, is rich enough to capture the true optimal policy, right? So in some sense, the optimal policy might not fall into this policy class that I give to you. But our hope is that maybe we can compete against the best policy in a policy class that I have, right? That I give to the learner. So for policy gradient methods, you can do that under a specific assumption. That is, we need to have a wide enough reset distribution. So let me just explain what it is. So if you look at this ratio, where the numerator is the state distribution induced by the optimal policy, the optimal policy in the policy class, not necessarily the true optimal policy, okay? And the denominator is the initial state distribution. So here, let's forget about that strong assumption on a delta initial distribution. Let's just think about simpler case where this initial distribution is wide enough, such that this ratio is a valid number. Okay, this ratio is less than infinite. So if you have this assumption, then you can guarantee that the policy gradient method will be able to find a policy that is as good as this pi tilde, right? The best policy that you could find in the policy class, which is not necessarily the optimal policy. Okay. But now you compare this policy gradient methods to other methods such as Q-learning, or this more generally this Bellman backup based approach. You will see that these approaches like Q-learning, they require stronger assumption. They require realizability in a sense that your function class, here the function will be Q functions. Your function class really need to be super rich so that it includes the optimal policy's Q function. Right? Remember, for policy gradient, we don't really require my optimal policy belongs to the policy class that I give to the learner, right? But here, for Q-learning, you really need to have something that looks like Q star, the true optimal policy's Q function belongs to the function class Q. Right? And for those of you who are familiar with Q-learning, except this realizability assumption, you also need something called Bellman completeness, which is roughly saying that if you take some function from your Q function class, right, a neural network from your function class, and you apply this Bellman operator on it, you get a new function, and you want to make sure this new function also belongs to your function class. So this is actually way stronger assumption than the sort of the distribution mismatch ratio that we see on the left-hand side. So one of the most successful story of policy gradient, I think, is this robotic hand manipulation project from OpenAI. So they were able to basically using PPO, a variant of natural policy gradient methods, to train a robot arm that can play this Rubik's Cube. I think one of the notable techniques that they use is this domain randomization. So in summary, so what they do is that they can create lots of simulations, lots of simulated robotic arm that has different kinds of parameters, maybe frictions, maybe weight, and so on and so forth. And they also can physically maybe perturb that object using some stuffed animal, for instance, right? So the goal here is to generate a wide distribution for different kind of configuration of the robot arm and different kind of configuration of the object. So in other words, the domain randomization technique is basically making this initial state distribution mu0 as wide as possible by either manually injecting perturbation using this stuffed animal, for instance, or by creating different kinds of simulations with parameters, with physical parameters sampled from a wide distribution, for instance. And this really makes this potentially, well, not provably, but potentially, this really could make this ratio to be as small as possible, or at least finite. Okay, so but policy gradient methods will actually indeed fail if your initial condition, that mu0, is not wide. So let's look into this super simple example. I have a huge long chain, and the agent always starts from the left-hand side of this chain. So the agent always starts from state S0. And so the agent has maybe 3 actions. 2 actions move the agent back to the left, and one agent move the agent, one action move the agent to 1 step right. Okay? And you get 0 reward along the chain until the very end of the chain. Okay, so in this case, let's initialize some policy that basically does random walk, right? So without any prior knowledge, the initialization we could do is probably initialize a policy that sort of uniformly picks actions among these 3 actions, right? Without any prior knowledge, this is probably the best initialization we could do. And if you start from that initialization, and you can compute the gradient with respect to that initialization, and you will see that the gradient magnitude is extremely small, in a sense that the magnitude of the gradient at this initialization point is really 2 to the negative of the horizon. So h here is the length of this chain. Okay, and this is not only true for the first order gradient. This also applies to higher order gradient up to I think h over log h order. So basically, if you look into the first order gradient, the magnitude is super small, and even if you look at the second order gradient, the magnitude is also super small, right? Exponentially small with respect to the horizon. So this means that if you start from that initialization, if you run gradient descent, you basically cannot find any improvement direction, right? So the learner just look around and she will not be able to find any descent direction, right? No matter how, no matter you're trying to search for the first order gradient or the second order gradient, third order, whatever, you just won't be able to find any descent direction. So this is really different from, at least the practical perspectives of supervised learning in deep learning, right? So in supervised learning, we often find the gradient descent tends to just work super well. And we now have lots of initialization techniques so that now the gradient descent performance is not really sensitive to initialization that much, right? And in supervised learning, we often see a picture looks like that, right? We have some saddle point, but if we look at maybe the second order information, we often be able to find a descent direction, right? So this is a saddle point, you're somewhere in the middle, and you look around, you will find a direction that you can descend, right? But you might have to look into the second order information. But as we just explained, this is not the case in reinforcement learning, right? So even at the first stage, at the initialization, I can get an extremely flattened region. And this is not only for the first order information, but this applies to higher order information up to capital H over log H. Okay. So this flattened region is really due to the lack of exploration, right? Imagine, recall the chain example that we have. You know, we start from one end of the chain and our reward signal is at the other end of the chain, right? You really have to figure out the right combination of actions that you can take along the chain in order to hit that goal. And without hitting that goal, you really get zero reward signal, right? So you basically get zero gradient. Okay, so let's look into this one particular example. And I'm going to show you some concrete numbers about popular gradient, policy gradient methods. So this example, in this example, we always start from the initial state as 0. And we're going to have two chains, chain 1 and chain 2. They share a similar structure. So both chain, they have, they are long in a sense that you have to sort of, starting from the beginning of the chain, you have to go through multi-stages in order to hit the end of the chain. And you only if you hit the, this orange state, you will get reward. So let's see you hit the orange state in the first chain, you get reward 5. And if you hit the orange states in the second chain, you get reward 2. Okay. And inside this chain, you have two kinds of states. So I'm going to call them survived state and bad state. So the survived state represented by a white circle here. So for these states, you have 10 actions to choose. And only 1 out of 10 actions will let you stay in the survived state. Basically, only 1 out of 10 actions will transit you to the next white state. And if you pick a wrong state, which in this case has 9 wrong states, wrong actions, if you pick a wrong action, you will be deterministically transited to the bad state, right, which is the black state here. So for this black state, this bad state, you will basically stay there forever, right? All the actions in the bad state will just transit you to the next bad state. So there's 0 probability you will be able to recover back to the survived state, okay? And to make the problem even worse, we're gonna add anti-shaped reward in this bad state. Whenever you hit the bad state, I'm just gonna give you a tiny, incentive. I'm gonna give you a tiny reward. So why this problem is hard, right? So we have obvious local minimum. So what's the obvious local minimum? So you start from an initial state, you transit to the first, survived state in either of the chain, and then you're just gonna deterministically pick one of the bad actions. You have 9 bad actions, and then you deterministically transit to bad state. Then along these bad states, you're gonna get tiny rewards, right? Along the way, all the way to the end. But this is a local minimum because you're gonna miss out all these orange states, which have, large rewards. And this problem, because we have 2 chains, we're also gonna have this catastrophic forgetting problem. So as we will show in the next slide, classic policy gradient methods, they will tend to just focusing on solving one particular chain, and they will forget to revisit the another chain. Because from a learner's perspective, there are 2 chains, but the learner has no idea which chain is better, right? So if the learner, in this case, only focus on to solve the second chain in this problem, it will basically forget to explore the first chain, which is a better chain in this case. So really to solve this problem, we need to force the learner to somehow solve both chains simultaneously. Okay, so let's look at the performance of some popular algorithm. So the first algorithm is PPO. which is basically natural policy gradient. So as we can see, if we set the horizon of this chain to be tiny, like 2, and then PPO is able to solve it, right? So if the chain is super short, if capital H is equal to 2, then PPO is fine. Doing random exploration, picking random actions at every time step to do exploration is fine. But once you get longer horizon, PPO basically fails, right? So imagine that the horizon is 10. What's the probability of a random policy can visit the end of the chain, the orange states, right? Which is roughly like, 0.1 to the 10, right? Which is tiny. And even if you apply more sophisticated policy gradient methods, such as PPO with random network distillation, which is one of the most popular practical methods people will use to solve actually exploration-heavy problems in practice, we can see that the performance definitely gets better. We were able to succeed around 50% of the time. So this is indeed the forgetting problem. Okay? So let me explain why this is the case in this slide. So let's look into the traces of R&D during training. Okay, so in this plot, I'm showing sort of the visitation ratio. The state distribution from R&D in both chains, chain one and chain 2. Okay, so let's see at the episode 500. So PPO with random network distillation, R&D, happens to visiting the first chain. So R&D is trying to explore the first chain. And then at the episode 3000, R&D is still focusing on solving the first chain. But around episode 3500, R&D sort of realized that there's another chain, so maybe I should spend some time on the second chain as well. And then around episode 5000, it just determines to completely focus on exploring the second chain. And indeed, in this round, R&D successfully solved the second chain, in a sense that you can see from episode 6000 to episode 8000, R&D really realized that a correct way to stay on the good states. Remember, we have the first two lines, the first two rows in each chain is a good states, right? So if you look at the traces in the episode 8000, so R&D is managed to stay on the survived states in the second chain. But then it has zero sort of probability of visiting the first chain anymore. So it really sort of remembers how to solve the second chain, but it forgets to go back to explore the first chain again. But in this case, unfortunately, the optimal chain is the first chain. So R&D just misses the maximum possible reward. So this is really a practical issue in my perspective, because when you run policy gradient methods, especially when you do this reward bonus algorithm, so this policy will quickly become very deterministic. And if your policy is too deterministic, then you basically don't have any chance of visiting a different state. Your policy, whenever you execute a policy, it always just generates the same trajectories over and over again. Okay? And the policy gradient methods really rely on randomness to sort of do exploration. But at the stage when you can solve the second chain, the policy is super deterministic. So in summary, so policy gradient methods has some common issues. So the first issue is the lack of the ability to do exploration. So this we observed from this this toy example where you have a long chain and we can compute the gradient magnitude of some initialized policy, and we can basically prove that the magnitude of the gradient is exponentially small with respect to the length of the chain. And then we also observe this catastrophic forgetting issue where when you train policy gradient methods, the policy tend to be very deterministic at the end. So you lose the ability to sort of explore, to go back to the second chain in our example, for instance. So this happens even with practical, very well engineered policy gradient methods such as PPO with R&D. right? Where you use some reward bonus to encourage exploration. Otherwise, you will not be able to solve one chain, as we observed from the performance of PPO. Okay, so next we're going to talk about one potential solution, which is our solution, which relies on the idea of building a policy cover and reward bonus together. So as we will see in a minute, so policy cover, this policy example, allows us to sort of remember the places that we have visited previously. And this reward bonus basically will allow us to, for instance, whenever we get to the one of the chain, this reward bonus will allow us to successfully explore the particular chain. But the policy example will allow us to sort of revisit the other chain, and then we can successfully solve both chains, for example. Okay, so before we dive into the algorithm, so here are some notations. So we have this Markov decision process, and we're going to define some functions. First, a value function, which basically says that if I add state S and if I follow a policy pi all the way to the end, what's the expected total long-term reward? Okay. And we also have this Q function, which basically says that if I start at state S and I first take action A and then I follow policy pi all the way to the end, what's the expected total long-term reward of this process? And we're also going to define a state action distribution. So I think details not really matter, doesn't really matter here. This state action distribution of a policy basically says that if you run this policy long enough, what's the distribution you induced over the state action space, right? So for each state action pair, this basically says that if you run your policy long enough, what's the probability of the agent visiting this particular state action pair? Okay. So basically, every policy induces a state action distribution over the state action space. Okay, so this policy cover, policy gradient methods, conceptually is very simple. It's an iterative procedure. So let's see we are at some nth iteration of this procedure, and we have computed pi 1, pi 2, all the way to pi n. So these are the previous computed policies. So we are not going to throw them away. So instead, we're just going to use them to form a policy example. And then let's see that we compute an average state action distribution by just averaging the state action distribution of each policy in the policy cover. Okay, so we take state action distribution of every policy in the policy cover, we average them. Okay, so we don't really need to compute this distribution, but for now, let's say we have this distribution available. Okay, all we need is just the ability to sample from that distribution, but we will get to that. So let's see we have this average state distribution. And now I can basically design some reward bonus based on the probability of visiting a particular state action pair, right? So for a state action pair, which can be represented or can be visited by the policy cover with reasonably high probability, I will assign small reward bonus. And for those state action pair that cannot be visited by any of the policy in the policy cover, I will give it a large reward bonus. Right? So we call this intrinsic reward. So in this cartoon image, so this darker green region basically represents that states that are underrepresented by the policies in the policy cover so far. And these lighter regions represent the state space that can be well covered by the current policy. And these red dots are basically representative state action samples from the policies in the policy cover. Okay, so I'm going to add large reward bonus on this darker region state action space. And now I'm going to do policy optimization using this intrinsic reward, right? Because I would encourage the agent to explore. So what I'm going to do is to randomly select a policy in the policy cover, and I'm going to execute that policy from the initial state for some time steps. When I get to this state action pair SA, then I'm going to switch to my current policy, the policy that I'm currently optimizing, right? And I'm going to roll out my current policy for some time steps to collect an unbiased estimate of the Q value, the reward to go of my current policy. And I'm going to repeat this process a few time steps so that I can get a mini batch data set that consists of state action pairs that is sampled from a random policy that I picked it from the policy cover and the corresponding rollout estimate for the Q function of my current policy at the particular state action pair, right? So here, all I'm doing is that I'm sort of trying to generate the data, generate state action pair at the frontier of the state space that is previously covered by the policies in the policy cover, right? And then I'm trying to do optimization around the states in the frontier of this state action space that can be covered by the policies in my policy cover. So the hope is that if I start doing policy optimization and the frontier of this state space that can be covered by the policy cover, I can gradually expanding my policy cover and then eventually hopefully cover the entire state space. So now once I have this mini batch data, I can just do simple least square, right? All I do is to try to find some function approximation f that can approximate the Q. And once I get this estimator f hat, I'm just gonna do simple policy update. So in this case, we use this mirror ascent style update for updating the policy. So once I get a new policy, I will just repeat this whole process a few iterations. So basically what I'm trying to do is to use natural policy gradient update to optimize this new Markov decision process. Here, new means that I'm designing a new reward, right? Every time I'm designing a new intrinsic reward for my optimization problem. And once I can solve this new Markov decision process reasonably well, I'm just going to exit this process and append the latest policy to the policy cover. And then I repeat the whole process again. Okay. So what are objective function that we actually optimize inside each episode, right? So we can actually write this down, right? So what we are optimizing is this objective function that looks very similar to the original objective function with two important differences. So the first difference is that we use policy cover rather than the initial state mu0, initial state distribution mu0, right? So here rho n represents the average state action distribution from all previous policies. So we're never gonna start from a fixed initial state. We're always gonna start from the state space that has already been explored by the policies in policy cover. And the second difference is that we also have this reward bonus, right? Instead of just optimizing the true reward, which could be extremely sparse, I'm adding this dense reward bonus as an intrinsic reward to motivate the agent to explore. So the policy cover will advise this catastrophic forgetting issue, right? Imagine that you have a policy that first tries the chain 1, and you have another policy that tries chain 2. Then every time you always have some chance of picking a policy that visits the first chain, right? We will never forget to revisit the first chain and to do optimization afterwards there. And this reward bonus basically allows us to get rid of this sparse reward issue, which will help us to do exploration. So now when specialized to linear function approximation, so this is the setting that we're going to focus on, and we're going to do some proofs for this setting. So for linear function approximation, let's see we have some linear feature vector, right? Which you can think about as some feature vector for state action pair. Let's see, for instance, some kernel features such as random Fourier features and so on. So we have this feature vector available, and we really want to use this feature to approximate our policy's Q values, right? So we want to use linear function approximation to do critic estimation. So again, we're going to form this policy cover. We have this average state action distribution, and this time, we're just gonna maintain a covariance matrix using our feature, right? So here, sigma n is basically representing the uncentered covariance matrix of my policy covers state action distribution. And now I'm going to just design a reward bonus such that for any state action pair whose feature does not align with the eigenvectors of this covariance matrix, for any state action pair whose feature does not align with large eigenvectors of this covariance matrix, I will give it a reward bonus. Okay? For those state action pair that happens to align with the big eigenvectors, I'm not going to give it any reward bonus. Right? So this is a thresholding. So basically, the idea is the same, right? I want to give reward bonus only to state action pairs that are underrepresented by the current policy cover. And then I can just do this row in and row out procedure that we described in previous slides to collect a mini batch data. And here I'm going to use this linear function approximator, this theta times theta dot phi, plus the bonus together as a whole objective, as an object to approximate the Q function. All right, so this is just for some technical proof reason, but in high level, I'm just using function approximation. I'm using this linear function approximation to approximate my policy's Q value. And with that critic approximation, I can just do this mirror descent style update. And then I'll just close the loop by appending the new policy into the policy cover. Okay, so let's look at an even specialized case, right? This discrete MDP, also called tabular MDP. So here, the feature will just be a one-hot vector. So you have S state, you have A actions. So you're just going to design this feature vector to be a vector whose length is number of states times number of actions, right? And all the entries of that feature will be 0 except the entry that corresponds to that particular state action pair. So you have a one-hot vector. And now let's take a look at what this covariance matrix would be under this one-hot vector, right? So this covariance matrix will be nothing but just a diagonal matrix where every entry on the diagonal is the probability of this state action pair being visited by the policies in my policy cover. And then you look at this this reward bonus. So we basically will give state action pair that has small probability of being visited by the current policy cover a huge reward bonus. Okay, so you just look at the number 1 over the probability of being visited by the current policy cover. If that number if the probability for state action pair, if the probability of visiting that state action pair is small, I'm just going to give it a huge reward. Okay. So what we can show for this PCPG for linear setting is that for this linear MDP, which generalizes this tabular MDP. So for this linear MDP, indeed, so the assumption is that the transition and the reward function can be approximated by a feature vector phi. So for those of you who are familiar with Hilbert space, reproducing kernel Hilbert space, for instance, you can just think about this transition P and this reward function. They belongs to the reproducing kernel Hilbert space with a predefined kernel and kernel feature phi. Okay, so if that is the case, then we can basically show that PCPG finds a policy pi hat that is epsilon close to the optimal policy with number of samples, just scales polynomially with respect to the parameters of the problem, especially this dimension of the feature vector phi. So as I mentioned, we can actually analyze this whole thing in reproducing kernel Hilbert space. In this case, my feature vector phi will be infinite, right? But here we can extend this result to reproducing kernel hero space by replacing this ambient space dimension D by the information gain from the information gain of the kernel. And so let's look at, what's the difference between this new policy gradient approach and the vanilla natural policy gradient. So in order to make sure vanilla natural policy gradients succeed, we really need to revisit this initial state distribution, right? So remember, we said that for vanilla policy gradient to succeed, you need to make sure that this initial state distribution is wide. So in this linear case, this wide basically means that the covariance matrix of the initial state distribution, state action distribution, needs to have a reasonably good condition number. So here the condition number is basically the maximum eigenvalue of this covariance matrix over the minimum eigenvalue. Okay, so we really want to make sure the initial distribution is wide enough such that the induced covariance matrix has a good condition number, has a finite condition number. And in this case, natural policy gradient actually will succeed without doing any extra fancy stuff. It will exceed with number of samples, scales polynomially with respect to all relevant parameters and this condition number. But as we mentioned in this TOEIC problem, right? For random initialized policy, this condition number could be exponential with respect to the horizon. And this basically means that if we apply this vanilla natural policy gradient methods to the toy chain problem that we were looking into at the very beginning of the talk, this condition number will be almost infinite, or 2 to the h, which basically means that in order to make vanilla natural policy gradient methods to succeed in that long chain problem, we really have to pay exponential many samples. So PCPG basically eliminates the condition number by actively exploring and also building this policy cover. Right? So this is basically the huge difference between this new approach and the vanilla natural policy gradient approach. Okay, so next I want to talk about the robustness of policy gradient methods to model misspecification. So before, we looked into this well-specified example, like linear MDPs, tabular MDPs, where everything is well-specified in a sense that you're using linear function approximation, and the things that you're trying to approximate, they happen to be a linear function. Or in tabular case, you're using table representations to represent the Q values or the policies, and table representation is good enough because you only have a finite number of states and finite number of actions. But now let's see, I have model misspecification. For instance, I'm trying to use linear function approximation to approximate my Q function, but who knows, my Q function might not be, linear in my given feature, right? So what would happen in this case? So specifically, we're gonna look at the difference between policy gradient methods and Bellman backup based methods like Q running. And we're gonna look into this concept of average model misspecification versus L infinite model misspecification. So let's just look into this one specific example, which is state abstraction. So let me quickly explain what state abstraction means here. So imagine that you have a huge state space. You have lots of states in your state space, right? So paying some polynomial sample complexity with respect to the number of states is too bad. But you happen to have some prior knowledge about the state space, and you know that some states, they look very similar. So maybe I can just group these states into an abstracted state. Right? So all I'm doing is that I'm using prior knowledge to do clustering in the state space. And basically the cluster provides me a map that maps from a state to an abstracted state. Right? So my hope is that the number of abstracted state, which is the number of the clusters here, is way smaller than the cardinality of the original state space. And by grouping all these similar states into an abstract state and operating in this abstraction level, I can find a near optimal policy by only paying number of samples scales polynomially with respect to the number of abstract state, right? The number of clusters. So this is the hope. But of course, when you start doing state abstraction, you cause this model misspecification, right? So we're gonna group very similar states into an abstracted state, but these states, they're not exactly the same. So the model misspecification is basically the disagreement between two states in terms of transition dynamics. And for any abstract state, we basically gonna define the model misspecification for that abstract state as the maximum disagreement between the transition of two states that are mapped to the abstract state. Okay, so in high level, abstraction reduces the state space, but introduces model misspecification. And if you look into those Bellman backup-based methods like Q-learning, you basically will guarantee to find a policy that is not optimal anymore, but you will find a policy that is close to the optimal policy, but the gap basically is scales with respect to this quantity. So specifically here, we have this max over all the possible abstracted state and action, right? So this is really what I mean by L infinity model misspecification. So, but what PCPG would give us is that we can really replace this L infinity model misspecification by this average model misspecification, averaged over the comparator policy's state action distribution. Okay, so of course, this L infinity model misspecification could be way bigger than the average case. So this basically says that, if you look into this Bellman backup-based approach, it's, you spend a lot of effort of doing state abstraction, for instance. You spend a lot of effort to pin down, state abstraction, but unfortunately, there are some part of the state space where you'll not be able to pin it down, right? So you get some big L infinity model misspecification. But if you just run this Bellman backup-based method, then you're gonna pay that maximum possible model misspecification. But if you look into PCPG, it says that I'm able to compete against a policy whose average model misspecification is small, right? So I probably will not be able to compete against the best policy because it's possible that the best policy may visit some state action pair whose model misspecification is huge, for instance, right? But let's see, there happen to be some near optimal policy that visits state action pairs whose model misspecification is tiny. Then I'm guaranteed to find a policy that is as good as that near optimal policy. So this is indeed a pretty nice property, right? This is the robustness. We are guaranteed to compete against the best policy in whose average model misspecification is small. And we can further look into this more contrived example, maybe, with linear function approximation. So here, we have this tree structure, and let's look at this green pass. So this green pass, let's say, gives me reward 1/2. Okay, and then for the subtree that is inside this dashed circle, I'm going to make this tree super deep. Here, I'm only showing you, depth 3, but imagine this tree has depth h. And I'm going to design features specifically now. This is the contrived part. So what I'm going to do is that I'm going to design feature phi such that phi S0 is the first standard basis and phi S1 is the third standard basis. So basically I'm assigning independent features for state action pairs along this green trajectory, okay? And then I'm going to design feature for state action pairs inside this binary tree such that the features could be arbitrary, but they will be perpendicular to the first, second, and third standard basis. Okay, so I'm really decoupled the representation, the linear feature from the green pass to the rest of state space. Okay, and then inside this binary tree, I can basically do arbitrary feature design as long as it's independent of the first, second, third standard basis, right? So in other words,
just as a heads up, we need to wrap up in about 5 minutes.
Okay, yeah. So basically here, features could be arbitrary bad, right? So model misspecification could be severe. But what you can show is that PCPG is indeed be able to find a policy that at least as good as the green pass. Okay, so it may not be find the optimal policy. The optimal policy might dive into this binary tree all the way to some weird places in this tree. There's no guarantee that PCPG will be able to find it, but PCPG guarantees to find at least a pass that has reward 1/2. Okay. But there's no guarantee basically for any other Bellman backup based methods like Q-learning, for instance. So just quickly visiting some experiments result. So for this bidirectional combination lock example that we looked into, so PCPG indeed successfully solves all these different horizons. So we basically able to visit every path, both chains successfully. And here is the traces. So you can see that I'm just plotting the traces of different policies in the policy cover. And you can see some policies, visiting different chains, like policy 11 visiting the first chain, so on and so forth. But you average over all these policies in the policy cover, you get a mixed policy that visits both chains almost uniformly. And if you start policy gradient methods from this nearly uniform distribution draw, you will guarantee to succeed. And another example is this reward-free exploration in a maze environment. Here, this is the state is an image that we feed it to a neural network, which is used to represent the policy in this case. And if you run PCPG, and if you look into the policy traces, we basically can see, different policies is trying to cover a different part of the maze. And when we average them together, we really sort of get a policy that can uniformly visit in different parts of the maze. And same for some control problem where we have extremely sparse reward. And if you run PCPG, and if we plot the traces of different policies in the policy cover, we will basically see that the policy cover is sort of uniformly cover all the possible state action pairs in the state space. And if you run policy gradient afterwards, you will guarantee to succeed. So to conclude, so we basically looked into the strong agnostic result for policy gradient. We looked into this average misspecification versus L infinite misspecification. And we have this polynomial sample complexity for well-specified cases for PCPG. And the idea of policy cover basically solves the issue of flattened gradient and also catastrophic forgetting. And lastly, this method, this idea of policy cover and reward bonus is really, I think is pretty practical in a sense that we have a lot of flexibility to leverage existing deep learning approach, deep RIO approach that people develop in the deep RIO community. So we can basically rely on this vanilla policy gradient implementation, and we were able to basically solve some extremely hard Atari games that requires heavy exploration. So that's, I think that's it. That's the end. All right, thanks.
All right, thank you. I'm clapping for everybody. Are there any questions? So we can do maybe one or so question in the formal question, and then we'll, as Palmer said, we can hang around and ask informally questions afterwards as well.
Yeah.
Actually, I had a question. The result about the misspecification where where you're looking at the average epsilon instead of the L1 epsilon. Did that strongly depend on the function space that you were using, like the linearity assumption, or was that general?
So I think you can make it general. Yeah, so in the paper, we actually do more general. We do more general analysis for any function approximation.
That's really amazing.
Yeah, well, but then you really, I mean, like, yeah, but for I will say for analyzing, because of the reward bonus that we are using, if you start using those general function approximation, then you need to sort of relying on more those weird complexity measure for function classes, for function classes like alluded dimension and so on and so forth. But for linear, you know, it's super straightforward. You just pay dimension d, right? So you get, yeah. So in a nutshell, you can do general function approximation, but you're gonna pay dependency that is associated with, you know, weird complexity measure for developed, like alluded dimension, for instance.
Yeah. Any other questions?
I have oh, go ahead.
No, go ahead, please.
Okay. You mentioned something about the condition number of the covariance matrix. And so it's the number of sample scales. Condition number. And you said you were able to reduce the condition number. So like in practice, did you find that the number of samples and the condition number really were very dependent, or was there some gap or?
Yeah. So, I mean, it really depends on the problem that you're trying to, the MDPs that you're trying to solve, right? So imagine you're trying to solve an MDP that is really similar to the long chain or the bidirectional combination lock that we're talking about. Then the condition number is really severe. Like if you run policy gradient, you're just not going to succeed with reasonable amount of time. Right? You really have to pay exponential many samples in exponential time in order to. Yeah. So in this case, I think it's pretty, you know, realistic problem in a sense that if you apply policy gradient methods to problems that requires heavy exploration, then they often basically gonna fail. Imagine, you know, you start from some initial state, you're trying to pick up the key, and then you can go to the door to open the door, and then you can come back, kill the monster to pick another key and go to the another room, for instance, right? So if you do a policy gradient, vanilla policy gradient, start from random policies, there is pretty much zero chance you will be able to figure out this sequence in order to succeed. So you don't get any reward signal, basically. Okay. But for benign problems, you know, problems that does not require, then policy gradient is perfect.
Yeah. You had a question.
Yeah, so when I'm curious, it's kind of like a general question because a lot of people do this. So one of the things you're doing is you are modifying the reward. And I wonder what it does to the behavior that you want to achieve, so like test time behavior, because you kind of like switch the problem a bit. So there's the interesting question of what that does to, you know, the agent that comes out at the end of it.
Yeah, so so I think one extreme case is this reward-free exploration. So let's say we just set the, you know, the true external reward to be 0. Okay, we just do reward bonus, then the behavior is basically you're just gonna explore everywhere, right? So you basically, you know, cover the entire maze. And now once you cover the entire maze, now let's see, you know, you give me an goal in the maze, meaning you give me a reward function, then I really basically know how to solve this maze afterwards, right? So you can give me a different reward function. I can immediately tell you a new solution and so on and so forth. But when you combine the true external reward and the reward bonus together, you're sort of doing this trade-off between exploration and exploitation, right? So, so once you explore the well, for instance, you know, this reward bonus, they will decay, right? Because in the tabular case, this is like 1 over the probability of visiting a particular state, right? So if, you know, the chance of visiting that state action pair getting bigger and bigger, the reward bonus will be basically threshold to 0. So at that point, you know, you're basically optimizing the original reward. So hopefully at the end, this returns you a policy that can optimize the original reward.
All right, thanks.
So maybe this is a good time to switch off the recording and start the informal session and give another round of applause to Wen.
Okay.